So welcome to part 3 of lecture 33. In the last part we looked at the complex spectral theorem, and in this part we want to look at the real spectral theorem. So kind of as I mentioned at the beginning, you kind of have to pay attention to where your vector space is defined, or where are you taking your coefficient. And if you're just saying that it's a vector space over the real numbers, then you also want to ask, okay, I have an operator, when do I know that I get an orthonormal basis of eigenvectors for my vector space V from the operator T? And it turns out that the operator can't be normal in the complex case. You have to actually have that T is a self-adjoint operator. So T is a self-adjoint operator. Okay, I don't know if you remember that, but that means that T star, the adjoint of T, is equal to T. Then V has an orthonormal basis, and the matrix can be diagonalized with respect to some orthonormal basis. Okay, so we'll go through the proof, but we're not actually going to go into complete detail for the proof. Okay, now the implication of B and C, again, it just follows from Theorem 5.41. Theorem 5.41, as I mentioned before, is just saying that, well, you know exactly when you get a diagonal matrix, right? It's if you have a basis of eigenvectors. So we're just adding the adjective orthonormal to that basis. Okay, so we haven't really changed anything there. The real heart of the proof is that showing A implies C and C implies A. And the proof C implies A is actually the easier part. And it's because we know, because this matrix is diagonal, we know that when you take the transpose of this matrix, okay, so there's kind of the T here means the transpose, because it's a diagonal matrix, you just get back the matrix itself, okay? And since we're working over the real numbers, the transpose of your matrix is equal to the matrix of, or I guess it's the same thing as the conjugate transpose, because there's no complex numbers kicking around, and this is the same thing as the matrix of the adjoint. So because this matrix here is equal to this matrix, and because this matrix is equal to this matrix, that implies that this operator is the same as that operator, right? So the operator of the adjoint of T is the same thing of T, so that just means that T is self-adjoint. Okay, so that finishes that part right there. Okay, now there's one thing that's left over, okay, which is A implies C. Okay, and so you should see the textbook for the proof. Okay, and you may be wondering, well, why not just try to mimic what we did in this proof? But when you try to mimic it, you get stuck right away at the beginning, because in the textbook there's no Schur's theorem over the complex numbers. Okay, so you can't follow this argument because you can't jumpstart at this stage right here. Okay, so that's kind of why the textbook kind of developed something completely different, because it has no Schur's theorem machinery in order to do this proof. Now, interestingly enough, there is a real version of Schur's theorem. Note, there is a real version of Schur's theorem. Okay, and in fact, if you pull out your textbook from Math 1B03, you can probably find the statement of Schur's theorem embedded in a homework assignment somewhere in one of the later chapters. Okay, that can be used. Okay, but this is not proved in the text. Okay, so the author decided not to use a real version of Schur's theorem, which is fine. That's his prerogative. Okay, but there's a very useful corollary, and for those of you that have taken 2LA3, you may have seen the real spectral theorem, but maybe you wouldn't have seen it expressed this way. The way that you would have seen it in 2LA3 is in terms of matrices, and remember, being self-adjoint means that you're talking about symmetric matrices. So this is what you might have seen from Math 2LA3, which is if A is a symmetric matrix, then A can be diagonalized. And if you're familiar with this terminology, it can be in fact orthogonally diagonalized. Okay, so so this is kind of very useful because this is even something we talked about in Math 1B03, which is in general, it's hard to just look at a matrix and determine if it can be diagonalized. You have to do kind of a lot of work, right, to decide if it can be diagonalized, right? So this is, even saw this in 1B03. But the point is the corollary, what it does, it gives a large class, where it is easy to determine if a matrix can be diagonalized. All right, so you just look at your matrix, and if it's a symmetric matrix, you go, yes, I know that this matrix can be diagonalized. And the reason you can do that is really because it's a consequence of the real spectral theorem. Because if the matrix is symmetric, that means if we think of it as an operator, it's self-adjoint, and so that this theorem tells me, yes, you can diagonalize it. Okay, so that's kind of a handy result and kind of ties back into something that you may have seen if you took the 2LA3 course, and definitely something you would have seen in Math 1B03 when we talked about diagonalization. So in the last part, I'm just going to talk briefly about what's called spectral decomposition.